Thank you for the introduction. I would like to thank the organizers for the invitation. Today, I'll talk about the spectrum of the Dirichlet Laplacian in some regions of the space called the sheared waveguides. A sheared waveguide is a region regions has in these pictures. I will give a precise definition of them later. And want to know information about the spectrum of the operator. If the region is bounded, we know that we know that the spectrum is purely discrete, so today I'll focus in the case that these regions are unbounded. So this model was inspired by this work. Here, the authors defined a new kind of strips called the sheared strips. A sheared strip is built by translating an oriented segment in a constant direction along an unbounded curve, as in the pictures here. So they studied by considering the Dirichlet Laplacian in these kind of strips. They studied the spectrum of the operator. They studied, for example, situations where the geometry can create discrete eigenvalues, situations where the geometry can ensures a type-hard inequality, and the situations where the geometry ensures that the spectrum is purely discrete even if the strip is unbounded. So, inspired by this work, I tried to define a similar region in the space R3 by translating a section along an unbounded curve. So here I will give the definition of a sheared waveguide. At first I need some notations. So A1, A2, A3 denotes the canonical basis of R3. S denotes a bounded, open and connected set of R2. A point of S is denoted by Y1 with coordinates Y1, Y2. F and G denotes functions that satisfy some regularity conditions, and from F and G we define the spatial curve R by expression in 1 with coordinates X, Fx and Gx. So geometrically the region S translates along the curve R in red here, so that at each point of R, S is parallel to the plane generated by E2, E3. So following this construction, we obtain a region as in picture 4. So this kind of region we call a sheared waveguide. From now on, I will call the region of by omega. So omega, we can parameterize it from this set, and we are going to use this notation for the Dirichlet Laplacian in omega. To study this spectrum, we start with this particular case. Here we assume that the derivative of the functions f and g are constant, beta 1, beta 2. In this case, the reference curve is a straight line, and then when you translate S along R, you obtain a region as in picture 5, you obtain a straight waveguide. So in this case, it's easy to know what happens with the spectrum. We know that it is purely essential, and furthermore, we know that it is the interval from E1 to infinity, where A1 is the first eigenvalue of the Dirichlet Laplacian in the cross-section S'. S' has in this picture, S prime is orthogonal to the reference curve R. However, we can also characterize E1 from the region S. So here we can perform a change of coordinates. So we obtain the operator in 5. It is an operator which acts in S, and it depends on beta 1, beta 2 in this part. And so we can see that the E1 is also its first eigenvalue. So we can characterize the spectrum in this way. And you have that, in this case, the spectrum is purely essential, and it is the interval from E1 to infinity. Now, the idea is to consider, from this particular case, to perform some deformations in a straight waveguide so that these deformations maintain the essential spectrum, but create discrete eigenvalues. For this, we consider a more general situation. So here we assume the conditions in 6. Geometrically, these conditions ensure that omega is asymptotically a straight waveguide at the infinity. So in this case, we have the stability of the essential spectrum when we compare with the previous case. So here the essential spectrum is also the interval from E1 to infinity. E1 is the same as before. It's the same as the eigenvalue, the first eigenvalue of the operator in 5. But at this point, we don't have information about the discrete component. To say something about the discrete component, now, at first I need some notations. Here we consider the function k, which is the eigenfunction associated with the eigenvalue A1. From it, we define the constants A, B, and C by 7 and 8, and you define the function V by expression 9, which depends on A, B, C, beta 1, beta 2, and the functions F and G. And then we obtain theorem 3. Here we assume the conditions in 6, that is, we are assuming that omega is asymptotically a straight waveguide at the infinity, so the essential spectrum starts from E1, and under the condition that this integral is negative, the integral of V is negative, we can show that the infimum of the spectrum is strictly less than A1. That is, the discrete spectrum is non-empty. In fact, we know that the essential spectrum starts from A1, and the inequality in 10 ensures that there exists a spectrum below A1, so there exists a discrete spectrum. Here I put the main idea of the proof. It's a standard strategy. We can find a convenient sequence PCN so that it holds the convergence in 11. So here has A1 is the infimum of the essential spectrum, and it has this integral is negative, just to take n large enough and to apply the minimax principle. I would like to try to detail more this proof. Just one idea. So here the strategy is to work with the quadratic form associated to the operator, which is the integral in omega, and here we have the gradient of PC, where PC is in this Sobolev space. Then we have our sheared waveguide, which has this geometry. Then we perform a change of coordinates in the region, which transforms omega in a straight waveguide. R times S, I will call it of lambda. And then when you perform this change of coordinates, the quadratic form changes too. So it becomes the integral in lambda. And here we have this expression, derivative of, I will use the same notation, PC, with respect to x, derivative of f, derivative of y1, derivative of g, derivative of y2, this term plus derivative y1, derivative y2. So I use x for the variable in R and y for the variable in S. So now we are going to work in a straight waveguide, and how information about the geometry of omega now appears in the expression of the quadratic form. Then the sequence. This sequence PCN that you take in the proof of in this proof, we use the function k, which is the eigenfunction associated to the eigenvalue A1. So we fix it. We consider a family of functions phi n from R to R, satisfying for each n phi n is in C infinity. For each n phi n is equal 1 for x in the interval from minus n to n, and phi n is equal 0 for how x in R except the interval from minus to n to n. And then finally we define PCN x y by phi n x k y. So we can work with this sequence to obtain the limit in 11. So by using that, k is the eigenfunction associated if E1, and by using these properties of the sequence phi n, this is the reason that we arrive in the integral of v in the limit. So this is the main idea. So here in this result, we have a kind of geometry that can create discrete eigenvalues for the operator. We can see that this condition is a sufficient condition, but it is not a necessary condition. And we can see that by this other result. So here we assume that the conditions in 6, that is, omega is asymptotically a straight waveguide at the infinity, so the essential spectrum starts from A1. And we assume that the derivative of the function g is equal 0. In this case, our function v stay only beta 1, 2, no, sorry, a derivative of f2 minus beta 1, 2. The function v reduces to expression here. And then, here we assume that this integral is equal 0, so the integral of v is equal 0, and you assume that the derivative of f is not constant. And from these assumptions, we can also prove that the infimum of the spectrum is strictly less than A1. So here we also have the existence of discrete eigenvalues. Here the idea of the proof is the same as before, to find a sequence so that we have a convergence as in 12. So here we can use the same idea, you can use the same sequence of the proof, of the previous proof, but we are going to find that the limit is equal 0. Then we perform a perturbation in this sequence. We perform a convenient perturbation, and so we obtain a negative value in the limit. So this is the main idea. So we have these two situations where we can ensure the existence of discrete eigenvalues. Now, if the waveguide is thin enough, we can find additional information about the spectrum. So here we multiply all points of the section S by a positive parameter, epsilon. Then we multiply the points of S by epsilon, and from now on you call the region of omega epsilon. By considering the Dirichlet Laplacian here, we can find additional information, and here we have this result, theorem 5. Again, we assume that the waveguide is asymptotically straight at the infinity, so in this case we know what happens with the essential spectrum. And here, if the waveguide is thin enough, it's sufficient that V assumes a negative value to ensure the existence of discrete eigenvalues. And in this second part, if V assumes a negative value, we can prove that the number of discrete eigenvalues increases when epsilon goes to 0. I will give the idea of the proof of the first item. So here, in this case, we are assuming that the omega epsilon is asymptotically straight at the infinity. Here, I will recall. We are assuming the conditions in 6, and in this case, we have this result about the essential spectrum. So here we know what happens. We multiply the points of S by epsilon, so here you have this additional term. The infimum of the spectrum is E1 over epsilon 2. And then, if you denote by lambda j the sequence corresponding to the minimax principle, for this difference, we can find this upper bound in the right side. And from here, we can see that if V assumes a negative value, then this difference is negative and has A1 over epsilon 2 is the infimum of the essential spectrum. We can ensure that there exist discrete eigenvalues. So this is the main idea in this part, to find this upper bound. Now here, about this model, I have two questions here that I couldn't answer yet. The first one is to know what happens with the spectrum if you are in the situation that when S translates along R, it can rotate too, so you would have a kind of twisted waveguide. And the other question is to know what happens in these situations here. So I don't know yet. Now I present another model. The second model was inspired by this work. Here the authors considered this kind of strip, a broken strip with a corner. And in this kind of strip, they studied the Dirichlet Laplacian. They proved that the discrete spectrum is non-empty. The number of discrete eigenvalues is finite, and also that when theta, which is this angle, goes to 0, the number of discrete eigenvalues increases. So inspired by this work, I tried to define a similar region in the space, R3, but following the same steps as the previous case. So here, we are going to work with this region called the sheared broken waveguide. Here, unless this corner, we have two half-straight waveguides, and you want to know if this corner can create discrete eigenvalues. The construction here follows the same steps as before, but I need to fix some notations at first. So here you fix beta, a positive number, and you define the curve R beta by 16 with coordinates x, 0, beta modulo x. So R beta is a line, a broken line in the space, as in the first picture. So the region S translates along R beta, so that at each point S is parallel to the plane generated by A2, A3. And following this construction, we obtain a region S in picture 10, so we obtain this effect has a corner. I'll call this region of omega beta, which can be parameterized by this set, and we are going to use this notation for the Dirichlet Laplacian in omega beta. We start studying its essential spectrum, but here we have the same discussion as before. So I put in the new notations now. So here we can see that the essential spectrum is the interval from A1 to infinity, where E1 is the first eigenvalue of the operator T beta, given by expression in 19, and is acting in S. We have here, it's exactly the same problem that you have before. Here, it's the same, but with other notations. So here it's easy to know what happens with the essential spectrum. And now, to say something about the discrete spectrum, we are going to use the fact that our region is a thematic region. So here I will define an auxiliary problem. At first I define this new region, omega beta plus. For omega beta plus, we consider the points of omega beta which the first coordinate is positive. So you obtain a region as in this second picture. In this new region, we consider the Laplacian with Neumann boundary conditions in this part of the boundary where we cut, and the Dirichlet boundary conditions in the rest. And we call this auxiliary problem of Dirichlet-Neumann Laplacian in omega beta plus. And the point is that we can show that the original problem and this auxiliary problem, they have the same essential spectrum and they have the same discrete spectrum. To see that they have the same essential spectrum, roughly speaking, is because they have, unless this corner here and here, they have the same geometry. And to see that they have the same discrete spectrum, the main idea is that if you have an eigenfunction of the original problem, the restriction is an eigenfunction of the auxiliary problem. And if you have an eigenfunction of the auxiliary problem, we can take its even extension and we obtain an eigenfunction of the original problem. So this is what says lemma set. So this is the main idea of the proof of theorem 8. Due to theorem 8, from now on, we start studying the discrete spectrum of the auxiliary operator, the Dirichlet-Neumann Laplacian in omega beta plus. For this operator, we can prove that its discrete spectrum is non-empty. So here, the main idea of the proof is a standard strategy, as before, to find a sequence PCN so that it holds the convergence into end. Here, the main point is that we can find a convenient sequence so that the limit here depends explicitly from beta. Beta, we recall that it is related to definition of the reference curve, and it is related to the inclination of the reference curve R beta. And so here we can see that as beta is a positive number, we found out here minus beta, key a positive number too, so we can apply again the minimax principle. So this is the main idea. From this model, here we have more two informations. We can prove that the discrete spectrum is finite, and in the particular case where S is a rectangle, here AB times CD, we can find an interval for beta, so that for beta in this interval, the discrete spectrum of the operator has exactly one value. So here I'd like to know if this result can be proved for a more general region and not only a rectangle by, I don't know the answer yet. And so the references, and thank you.